Welcome everyone. So today is one of the weeks when the stuff should finally culminate, and I was looking forward to today's and the next lecture. So I should say that this is the second last lecture because next week there will be a lecture, and also in January. So, but yeah, end of
So when is the last one?
In 2 weeks. Yeah, just
So
before Christmas.
17.
Yes, that's right. But I think we are doing well, so I think we cover already a lot of ground, so I think there will be enough material. Okay, so let me recall where we stand. That's fine. So what did we do? On various levels we talked about supermanifolds. So supermanifolds. And last time we started working in coordinates, and now that we understand how to do things globally, so to kind of proceed faster, we switch to coordinates instead, and we just said that supermanifolds are spaces that have two sets of coordinates on them locally. Some of them are even, some of them are odd. And we also made sense of this formally, so this was really underlying some like topological space of manifold, and this thing is kind of the extra datum encoded in terms of sheaves. But for now, let's just think of it as coordinates. And we talked about how to build various other things, such as vector fields, which again you can define more in a coordinate independent manner. But for us, they were essentially expressions of this type. And similarly, we talk about differential forms. And these were generated by the following symbols, so the coordinates, these things, and then their differential. And on this thing, we had the action of the Derham differential, the Lie derivative with respect to such things, and contractions, and stuff like that. This is the only thing that you will need today. No, that's not true. But anyway, for now, let's stop there. And then maybe a couple of definitions, which I think I haven't done the last. I thought I did them last time, but I probably didn't because I couldn't find it on the video. So let's define the last ingredient before we pass to the next topics, and that's a symplectic form. So I will define both of them at once. So an even or odd symplectic form. This is two definitions in one. It's not like I'm not defining what even / odd symplectic form is. Definition of even and definition of odd symplectic form. So a supermanifold is a closed, with respect to this V guy, non-degenerate form. And now, if you want to make sense of non-degeneracy, then you can say that the symplectic form, the two form, it gives you a map that goes from vector fields to one forms, and you want this to be an isomorphism. And sorry, I forgot. Two form of either even or odd parity. Okay, so for instance, if I would take these things, and you can imagine a two form which would look like, I don't know, for instance, something like this. So one example, I mean, it would take like this would be R1/1. So you can take something like this example. And this thing is odd because this object here is even and this object here is odd. Sorry, the other way around.
This is odd, this is even.
Sorry?
Odd and even.
Yes, thank you. This is the first bit is odd and this is even. And also because it's a sorry. Okay. Also because it's a two form, then these carry some parity, but there's two of them, so they don't really contribute. So I can just count the parity of the coordinates. So even plus odd, and this will be perfectly odd. And then you can have stuff like R0/2, and you can say that you have, and this will be even. For instance. Okay. And one last thing that I wanted to mention is it's kind of a good thing to close with. So there is a kind of supermanifolds come always equipped with a particular special map. So for any supermanifold, I mean they come equipped with the identity map, but that's not very useful. For any supermanifold M, there exists a natural algebra map which goes from global functions into themselves and is given by taking a function and multiplying it by -1 to the parity of the function. Yes?
So if you wrote this second example, this R0, 2, if you wrote it for 0, n, and you would have like matrix with I, xij, that one would be symmetric,
Yes.
I guess.
Yes.
So it's not necessarily kind of given by antisymmetric data because of the parity.
Yes, that's right. We will see that example later on. But exactly, yeah. In fact, yeah. Okay, so first let's check this claim. So I'm claiming that this is an algebra map. Check. How do you check if something is an algebra map? You apply it. You have two functions, and you have product, and you apply it to both of them, or you apply it to the product directly. If I do this and then multiply them, is it the same as if I maybe let's give it a name, sorry, I think it's maybe better. Let's call it something. Control, there it is. Let's call it pi, lowercase pi. Then what we want is that, and technically pi star, because it has some function. So all we need to check in order for it to be an algebra map is that is it true that this thing equals this thing? And yes, it's true because the first thing this is -1 to parity f, and this is -1 to the parity g, and this is -1 to the parity of f times g. But parity is additive, so if I multiply two functions, I mean, this is the sum of the parities. I multiply two odd things and I get something even. So it's true. So this is an algebra map, and then if you remember by one of the proposition that we discussed before, the one that told you how to describe maps in terms of coordinates and algebras of functions, then this thing is equivalent to saying that there is a natural map on the manifold. So this corresponds to this corresponds to a map from M to M called parity operator. Okay, if you remember, there was a statement that maps of two supermanifolds are in one-to-one correspondence between the algebra maps on their global constants. And okay, and maybe just to have something like how does it act on coordinates? So looking here, it fixes the even coordinates and it adds a sign for the odd coordinates.
So you can think about it as an inner vector field without forces Z2 parity. So it multiplies homogeneous components.
Yes, but
But inadditive.
Yeah, it's like a finite version of that. Yes. And again, we will talk about that in a second.
Sorry.
I mean, no, it's good to say. No, I mean, not really about that, but about the related thing about n manifolds, where there will be. But yeah, very good. Yeah, so this is like a finite analog of the Euler vector field, which we actually haven't talked about yet, only in the context of differential forms, I think. But we will get there in a second.
If you had a vector bundle and you would associate to this fiber directions the odd coordinates using this pi, then it's just acting as -1 on the fibers, no? Like geometrically.
Yeah.
Yeah, so it's like reflection in fiber.
Yeah.
Inversion.
That's right. Okay, that's nice. Yeah. Yeah, so yeah. Hopefully that was audible. But yeah, you're saying that if I take a parity shifted vector bundle, then this thing actually just tells me that I'm reflecting with respect to the identity, with respect to 0
Intersection.
on the fibers. Now, like a control question, what is the underlying map of manifolds for this guy? It's the identity on M on the body of the manifold.
But now maybe no star because it's.
Thank you. Okay, any questions for this part? This was just to close up some, or tie up some ends from the previous lecture. Now let's get to the more entertaining stuff, I would say. So now that we know about about supermanifolds, now we will talk about some sort of enhanced story. I will call this n-graded geometry. Where, okay, maybe I should specify at the beginning that, I mean, I don't care about what conventions people use, but I mean, here I will, this is what I don't mean by n. I include 0. So non-negative integers. That's what, n stands. Non-negative. No, it doesn't. Okay. Anyway, so what have we done so far? Ideologically. So we talked about supermanifolds. Which were spaces whose algebras of functions carry the Z2 grading, the parity. So whose algebras of functions are Z2 graded. No, ordinary manifolds would have, or ordinary topological spaces would have algebras of functions which would be commutative and no grading. These ones are Z2 graded and graded commutative. Okay, and so now what we want to do is, okay, so what we noticed, however, was that some spaces, they had a sort of a richer structure. So some spaces, namely one of our protagonists, which was the parity shifted tangent bundle, actually carried more structure. So it had an N, or if you wish, the Z grading. Right? Because we knew that the algebra of functions of this guy was simply differential forms. So on M. and this thing has a natural grading. And so there is actually more stuff in the game. So so there is a sort of like a higher, there's like a bigger group in question, and the Z2 grading can be obtained by the natural map that goes from this to Z2, where you just remember the parity. So now we want to formalize this. This was already formal, but like I want to just make a definition of such a manifold that would be kind of n-graded. So formalizing this idea, we get the following stuff. So there is, so okay, let me say as follows. So there is a way. One thing that people study often, and for which we have an expert here, is the story of when you want to pass to Z grading, and this is for instance necessary when you want to do stuff like PV, or well, okay, no, it is related to that. And okay, so but we will be focusing on a sort of other the n grading story, in which case I would call it n manifold. This thing will have n grading. They sound similar. I mean, not really close. They sound similar in difficulty, but or in spirit, but they're kind of sort of different in spirit. And this thing is also important, but for now we will focus on the n manifold approach, and I will adopt the approach taken by Chevera. So for now, let me just say that this n. The way to remember this is to say that this is non-negatively graded. So this is not bold. This is proper n in the Latin alphabet. Capital letter n. Is this clear? Distinction between these. Okay.
But is there like big difference? Isn't this n grading special case of Z grading? So
well, it depends. Well, if you define these notions somehow, then you can ask that question.
yes.
I haven't
Okay.
defined it.
Will you?
No, and in fact, I mean, okay. So there is like a definition of this that I know, and there's a definition of this that I know, and I don't know from the top of your head. Or I don't know actually how to relate them. So they are kind of different in spirit, but morally they are, as you say, like one is kind of like a special case of the other. But okay, but it very much depends on which definition you adopt for these objects. So okay. So this was kind of the idea. Now let's be more precise. How do we do this? We will focus on the n-graded story. And I decided to split it in two parts. So I will first tell you an informal way to think about it, which is the one which is kind of useful to know and that you typically use when you work with them. And then I will give you a formal definition afterwards. I think this is going to be the most interactive way to do it. So informally, the first bit. So, an n manifold, at least once write it for manifold, is a space. This is an analogy to what actually this is what I just said about it. It's a space described by coordinates let me call them YA of potentially various degrees. Various degrees. And I will call these degrees deg YA. And this thing will be in n. This is in 0, 1, 2. And the way they interact is the same as for supermanifolds. So if I have two of them, then I can commute them, and the price I pay is given now by the degree. Is given that is determined by the parity, and parity is induced by the degree. So I need to take -1 to the product of the degrees. So on this level, it really means that I'm just taking a supermanifold and I'm assigning not just parity, but I'm lifting the parity of the coordinates to some integers or non-negative integers. Okay, kind of the most important example is now the case of differential forms. So differential forms, I can see them as functions on a varied manifold where I take this to be of degree 0 and this guy of degree 1. That corresponds to the stuff above. I won't write, I will give you that name in a second so far. I just want to write it like this. Okay. And then in this continuing in here, I can say that okay, just now we know how to do stuff in passing from manifolds to supermanifolds, then the things kind of become essentially automatic here. So now we can define again vector fields, forms, differential forms, etc. So all of the stuff like the one here. And the important thing is that now we can use the discussions from before. So signs are determined by the discussion we had for supermanifolds. Determined by the supermanifolds discussion before. So there we don't have to do anything new. Any questions? I need to erase this. Ideal time. So there is a couple of new ingredients in here. As was mentioned before, there is the so-called Euler vector field, which was not naturally existing on a supermanifold, but it naturally exists on these guys. We also erase the log. Please, any questions? Comments? I see everyone is tired at this end of the week.
End of ZQ.
Sorry?
End of ZQ.
End of the. Oh yeah, that's even maybe more appropriate. Was anyone else also surprised that the year is at the end?
I mean, it was to be expected, no?
Well, I mean, in terms of calendar year, yes, but I mean, in terms of teaching, it was kind of surprising for some reason to me. I always thought we are like in the middle of the semester. Well, not very always. Okay, well, thanks for the questions. I realized this in the beginning, so maybe there were not very many questions, but I did not give you anything to complain about this. So what is the new thing here in this n-graded world? So So we have this Euler vector field. I will denote it E. And the way it acts on functions is that it returns the degree of that function. If the function was of a concrete degree of function was if f has degree deg f. Okay, so how do we see that it's a vector field? Well, you can check that it acts, if you act on a product of functions, then it respects the Leibniz rule. Differently put, you can say that you can write it in coordinates by simply saying that you sum over all the coordinates, and each time you remove a coordinate, you add it back, and you multiply it with the degree of that coordinate. Okay, so for instance, coordinates of degree 0 actually don't enter here because they are multiplied by 0. Okay, so for instance, e.g. on differential forms, we have that E is simply psi alpha partial psi alpha. And here I'm not even writing the sum symbol because there is a proper summation over up and down indices. Okay, and so when talking about stuff, we need to talk about maps of the stuff as well. So what is a map of n manifolds? Well, this is the informal part of the discussion, so let me just say that this is a map of supermanifold which in addition respects the degree. So this is required to preserve the degree of functions. And now about the notation. So let's say, okay, the main source of examples. This thing is a vector bundle. Ordinary vector bundle. Now we can define the n manifold, which will be denoted vector bundle, and then n in square brackets. So this is called the shifted vector bundle. And how it is defined? Suppose that here you had some coordinates of degree 0 and you had some, these were coordinates on M. And suppose that we had T alpha, which were linear coordinates on the fibers. In other words, these are corresponding to some frame. Frame E alpha E. So now what I do here is that this new space will have now the same coordinates. They look the same, except those things will have degree 0 and these things will have degree n. And maybe a couple of notes. First note is that for notational convenience, when you shift the tangent and cotangent bundle, shifted tangent cotangent bundle, we simply write T m m or T shifted m of m. Okay, so it's kind of similar mark, but I mean, you might expect that we would call this Tm and then square bracket m. But in fact, no, this is the notation. That was not very deep. But okay, so the second thing, a way to remember things. So think of this thing as shifting the corresponding vector space down by n by n. So what do I mean by this? So if V is a vector space, let's say, if V is a vector space, then Vn is a graded vector space. With non-zero component in degree minus n. Okay, so for instance, if you can see V as sort of like this, you can see any vector space as a graded vector space if you just suppose that you have zeros everywhere else. Okay, so this is degree minus 1, 0, 1, etc. And then if you shift it, let's say by 1, then the new vector space that you get will have a V here in degree minus 1. Okay, it goes like this. And
So-
hence,
So like the ith component is the I plus n?
yeah, so the Vn, and then ith component of that is the that's maybe better to say. Like this is how you shift vector spaces. This is the definition of graded vector spaces. And the reason it plays well with what I wrote above is that the coordinates live in the dual space. So if you shift the space down, then the coordinates which live in the dual space are supposed to be pairing with your stuff to something in degree 0, so they need to be opposite. So then this implies that the coordinates are shifted up by n. Okay, this is why it makes sense. So the thing to remember, this is just to clarify or potentially confuse everyone. So the thing to remember that if you put n in these things, you'll have degree n. Yes?
So you haven't like formally defined these things.
Yes, not yet.
Yes, but I suppose an manifold is a supermanifold in particular.
Yes. Well, here I have in the definition I will give in a moment. Yes.
Right. So if you shift the vector bundle by an even degree, then you get a supermanifold with only even coordinates.
Yes.
But isn't that just the manifold?
Yes. That sounds correct to me.
Right.
Yes. 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 I agree.
Okay. No, it just seems weird to me that
You
you
can-
can have a known manifold with coordinates that degrees.
No, that's kind of not that. I mean, you can have like Euler vector field on like a normal manifold. Like for instance, you take like tangent bundle shifted by 2. You just define a vector field going in the fiber coordinates.
Okay, because I was sorry.
No, this is very good.
I thought right. If you shift tangent bundle by 2, then the functions on this shifted tangent bundle are just by definition of the graded manifolds polynomials in the 1, 0, which are like a different algebra of functions than the function is on.
I see. Yes, that is true. So in this informal section, I was going to skip over this, but in the formal one, let's see how it works. I think in the section that comes later, I guess you will define the function there to be arbitrary, not polynomial, but they would come out to be. We are not there yet, but if I go to the formal bit, then of course I'm not going to define formal. If you shift looks like, but I think the shift there is defined. The only meaningful way for the shift there is to be defined is that you take that to be really like a normal manifold. So there is like arbitrary dependence in this degree 2 things. So functions then will potentially have infinite degree. Yes. Maybe I'm talking nonsense. Let's see where we get there. It's a very good point. It is. Yeah. This is the point where yeah, like to make this stuff formal is not like it is a bit. There is no trivial amount of work you need to do, and potentially there are other approaches, and they are maybe related in non-trivial ways. Okay, so, but let's get there in a second. But just to finish this part, there was. I just wanted to finish the definition by saying. Okay, so we define an n manifold, so let's define something else. Let's define an nq manifold. So this is n manifold with a degree 1 vector field q, that q squares to 0. Because sometimes this is called cohomological vector field, or even some people call it just homological vector field, I guess. Although, strictly speaking, you would need to invert the degrees to make this homological, but anyway. Let's do this in parentheses. Some people just call it Q. And an example, the main example is the one that we are dragging with us. So this is the shifted tangent model. So now we gave the name. So this is the space whose algebra of functions is given by differential forms. And the cohomological vector field is a theorem. So this we've seen before. So this is just looks like this. So it has two types of coordinates, xi and xii. Maybe I called them alpha. I don't remember now. But better. This is the theorem. This is kind of the most important example to have in mind. Oh, okay. And there was one more line that I wanted to do. So, so a map of nq manifolds is required to preserve both degree and q. Okay. Any questions? Now we will go to the formal one. One thing. So now let's do it formally. So now we know how to think about the objects, sort of. Now let's try to make this formal. And okay, I will denote this with a star. Meaning that it's like for imagination it's often, for the exam I won't require this word. But it's kind of interesting story. So here I will follow the approach of Chevera. And before giving the definition, let me lead you to the definition. So let's see how the stuff actually, what is happening here. So the idea is to look at the motivating example. So let us examine the main motivating example. And let's try to abstract the properties from there. And so these are the differential forms. So differential forms. And now you might remember that there was this kind of part over which I went maybe a bit too brief, but it will be useful in this kind of ideological part. So recall that there was this funny way to see differential forms. that this parity shifted tangent bundle. Okay, so we don't. Let me go back to the supermanifold notation. So where we don't have parity manifolds, supermanifolds. So this parity shifted tangent bundle, we saw that there was this clever way to see it as maps from the odd line, so from this space into M. And because these are maps from somewhere to somewhere, or maybe some enlarged space where I allow some supermaps. So this thing carries an action of the diffeomorphism group of this guy. Okay, so there was that part. It was a little too brief, I remember, but the idea was just to extract what you know in ordinary manifold theory. If you have two manifolds, then each time you have a diffeomorphism of the source, you can recompose the maps and you have an action. It's a right action of this group. And in our case, there is this underline, so this thing was actually a Lie supergroup. And there was this kind of explicit description of it. If I call the coordinates on the odd line theta, then there was this kind of thing that I wrote before, is that you allow changes of coordinates that. Okay, so if we remember how we discussed this, we said that you want to allow changes of coordinates. If this would be not underlined, so you would only do ordinary maps from R0 to 0, 1 to itself, then you could only have these guys for some A, which is supposed to be a non-zero real number. And now adding the underline, we saw that there was a way to kind of see this as adding essentially some extra bit, and that these two things could be seen as an even, and this is an odd coordinates. On this diff. So this diff was a space that had dimension 1/1. So we have one even and one odd coordinate. And okay, this is this kind of underlying story of internal home. So let's just go one step before. Let's just talk about the ordinary, about the base of this guy, which we know is just the ordinary diffeomorphisms of the line, which, as I said before, is simply these maps that correspond to this, where this thing is non-zero. And this thing is just an ordinary Lie group, and it's the real group of like integers, sort of real numbers without zero. Is it star or cross?
Cross.
Cross. And let me emphasize that as a group, it's a multiplicative group. If you compose the two such things, then the corresponding A is multiplied. Okay, so there was some complicated action of a supergroup, but in particular, this space carried an action of this guy. And if you remember that that this was the thing that this is generated by the Euler vector field on differential forms, or like this thing generated. Like the action of this is generated. Sorry, the action of R cross is generated by the Euler vector field. Okay, so if you remember before that we said that this is some complicated space, but on the infinitesimal level, this corresponds to a Lie superalgebra, which has two generators, one even and one odd. And the even generator, which is the generator of this even part of the supergroup, this generated the Euler vector field, and the extra guy, this odd guy, is generated the Derham differential. But for now, let's just remember the first part. So in particular, so you have like action of this thing, some sort of scaling, and it's generated by the Euler. It's generated by some vector field, and this vector field, when it acts here, this gives the Euler vector field. Okay, does that make sense? The odd bit gives Derham. Okay, so now this leads to the following idea. So can we define n manifolds? The fact that I'm formulating this as a question might lead you to suspect the answer. can we define n manifolds as simply supermanifolds carrying the action of this guy? Maybe that's a good definition. So this thing in particular does have that action. Is this a good? Does anyone see an immediate problem with this guy? Or I mean, maybe there is no problem. Maybe this works. So there is one problem, and that's the fact that this thing doesn't talk. I didn't specify in any way how this acts. Like how is this compatible with the parity of the generators, like even and odd? But there is even a more fundamental problem with this thing. Is there any? Does anyone see by any chance? I see people are thinking. That's great. So any ideas? So what will be the idea that if I define this like this, okay, so what would this mean? This would mean having an action means that I would have a map on the. This would mean that I have a map like this, which, as we know by that proposition, this is the same as saying that I have a map in the opposite direction on the functions. Global function, let's say. Global on m times r with 0. Okay, so satisfying some properties that is, compose it in a compatible group structure. Okay, so maybe can we define n manifolds as this, and then define and use this to define and define function f to be of degree n if under this pullback, okay, if it maps to t times n times f. Okay, so this is how it goes in here. So the way Euler vector field acts on functions is that it multiplies the function by the degree. So if I integrate it to a group action, then this is what I get. I should get like some finite t to some n. This is how it works for forms. So I can now ask the same. So like if I have an action of this guy, so which means that I have a map from here to here, and I call this coordinate t, this coordinate on r, then I can declare the function is of some degree if under this map it sends to to itself multiplied by some t there. Okay. Question. Can I do it? Can I do this? What would go wrong if I did this? It's just some Lie algebra, very simple Lie algebra representation problem. It has to do with so what is this? If I do this, what is this n? Where does it live? Oh. No, it could in principle be any real number. Right? If n would be any real number, then this thing would be it gives a well-defined representation of R star. So the problem with this guy, this was not supposed to be easy. But the problem here is that this would not impose, like here a priori I could have n to be any real number. So answer this well-defined question was no, because this would allow n's which are not integers.
But what about if you replace compactified because it's circle action? Then it will be no problem.
If you do that,
So the problem here is R is not compact. So the one action should work.
yeah, but U1 has the okay. So, but okay, good. I did not even that didn't even occur to me. Yes, that could allow this to be in Z in principle, right? But the problem with that is, if there is any problem, is there any problem with that? want to say that it's a problem with like. No, wait. What was the problem really? So if you would have a circle action, then. Wait, I'm confused. But I mean, no, but the problem with the circle action is that then it would, I would need to kind of complexify this story somehow, no? Because I would need this multiplied, like the one-dimensional, like eigen stuff of that would have to be complex. It's a very good idea, I like that. But for some reason that I didn't think about before, it shouldn't work, but I guess this is maybe the reason.
So it should work at least in the analytical procedure.
Sorry?
It should work in the analytical procedure.
Maybe, yeah. Nice. But yeah, so the idea by Pavel, I think, is the idea by Pavel is that it's different. So, but similar in spirit, you replace R star by something different. Like, yeah.
Maybe I can turn around the question. So why if in the standard example, if the Euler vector field is kind of quantized, it has a kind of quantized eigenvalues in some instance.
Okay.
Why does it generate R cross action and not something compact? I guess it has to do with grading a usual vector field, even manifold, and quantized. I don't know.
So, so if this would be a Lie, ignoring some completeness or something, like if this would be just a Lie algebra representation question, then the representation of Lie algebra always leads to the representation of the connected, simply connected group corresponding to that. So that, which in this case would be R positive, like R positive.
Okay. Okay. Not too long, for example. Okay. Right. I'll think about it.
Yeah, no, for circle, you would, yeah, no, I mean, if you want this some real representation to lead to something that's connection of a group which is not simply connected, then the representation would need to be, I mean, the setup would need to be special. Some conditions would need to be satisfied. So what it uniquely gives is the representation of the connected, simply connected group, which in this case would be R positive. There is a -1 in there that. Sorry.
There's this. Yeah, this R star is two components. Kind of, so.
Yes. So maybe it's a good place to mention this. Like the
But it's not clear why the negative one is.
no, but here the negative one, like okay, in this action, if you take -1, this is an important point in the
This
this thing acts by yeah. Actually, maybe the ideal point to mention this was precisely here. So thank you, very good point. Thank you for mentioning it. So this is the parity operator. And you can, this thing you can allow you to kind of extend it to the whole R cross. I mean, if you would start with the whole vector field, I mean, anyway, it's what it is. Okay, so now what is the idea? So now recall again.
Sorry, and why did you say that this is wrong? Like if
oh, because you want it to be because in the informal part we defined this something where the coordinates are non-negatively graded. I didn't say integers. Non-negatively. Yeah, so like I want to keep some definition that kind of only has that kind of built in.
Okay.
Yeah, sorry, there is no big reason that this. I don't know. I was deciding what to present this. I think this was kind of okay. Maybe.
Like you want action of R star, and you say, okay, this allows all real numbers, and you say, okay, but our example has only integers, so let's stick to the ones that we see in the example. Kind of.
Yeah, but I want to give it like kind of definition that only has things and things that are similar to it in a sense that they have Z grading and not arbitrary. Yeah, it was not a very well posed question that I'm aware. Because we want to generalize this anyway, right? We want to get something more general, so I didn't exactly tell you in which direction. So in principle, this was a very bad question. So yeah, but well, what can we do? So okay, so there was so remember that there was apart from we have this diff R01 or the corresponding internal home, and this thing lived in something that was slightly larger, just like very slightly larger. So it lived inside all maps from the odd line to itself. And underline. Okay, this was if you want the coordinates again, this was a map that told you that this and this is in principle any, not necessarily it could be 0. So this is even, and this is odd. So it's the same. It's like the same as before, except that now we have R, the full R. Now this is not a group, because you can have a map that maps everything to a point. You allow A to be 0, but it's the next best thing. So it's a monoid. So this is a monoid, or in this case, okay, since I talked about the underline, it's a really super monoid. What does it mean? It's like a group except there is no inverse. Okay, so it's like monoid group. Like, this is the worst possible definition. Like a group, but without the inverse.
And I guess it's like supergroup.
Yeah, that's why I wrote again monoid. Yeah,
Okay.
without inverse. You see, I'm prepared. Or more formally, it's a category on one point, which is actually exactly what you see here. Like this thing is okay. Anyway, it's this like a group, but we don't impose inverse, so we still have identity. Okay, and it's super. So it's like it's in this space, and there's a map from the space times itself to itself, satisfying some conditions. So we need to categorically say what this is. Just think of it as like a super extension of this. Okay, and monoids have well-defined actions. I mean, it's just like you have group action. You want that they are composed correctly. And what is the body of this guy? Well, this is easier to answer because that we've already talked about before. This is simply the home without the underline. And by the proposition, this was simply, you give me a function, an odd function for each coordinate here, so it's precisely theta prime equals a theta, where a is any real number. So this is real numbers with multiplication. Because again, if I compose two of them, they compose multiplicatively. So we have this strange object, a real numbers with multiplication. It's not a group because 0 doesn't have an inverse, but it's a monoid. It's a fine object in principle. And should I have said this? Maybe. Okay, just for those, maybe I could have said this thing in the ordinary language. So if you want to have like, if x is topological space, then maps from x to x are monoid. This is what I'm generalizing this to the superset. Or in fact, doesn't have to be topological, so any category. Like if you have category and look at maps from object to itself, this is always a monoid. Okay, so now the idea is that now, if I would say that I have a supermanifold which carries an action of such a thing, carried an action of this guy. Okay, so far we're only looking at the bosonic, the even part. So you're free to forget about all the internal homes and everything. It's just like, what would happen if we would, instead of having an action of R cross with the product, we would say, we would take the full R. So, then the possible n can only be non-negative integers. Can only be non-negative integers. And why is that? Since otherwise, this thing that we have on the right hand side, Tn times f, this would not be a smooth function. It would not be smooth at 0. And you want this to be a map, that goes from functions to functions, in this case smooth functions, so, and this thing is only smooth if this is a non-negative integer. So adding the 0 solves the issue. It is kind of the idea.
But the operation is still it's still multiplication. It's
Yes.
yes. So it's still but it's still okay. Now it's not R times because that would not be group but monoid. So you exclude the include the 0 element and you multiply.
Exactly. Yeah. So now we can write formal definition. So definition and manifold is a supermanifold with an action of the monoid. I can drop left and right because this monoid is abelian. Action of this. And in Greek bracket end, but I will require also such that -1 acts as a rarity operator, which, if you remember, is canonically present on any supermanifold. And the reason I want that is to kind of make the two gradings compatible. So, where is it? Okay, so the last bit here. So this is to ensure, this is to have the induced Z grading coinciding with the supermanifold grading. Coinciding with the Z2 grading on the supermanifold. If you want to study n supermanifolds, you can forget this, and then you would have a sort of supermanifold which has an additional grading. But we only want to have n grading, so I will include this bit. Okay, so but again, an example. So if f was of degree n, which means that under our action we map this, then how does the -1 act? I just substitute -1. So I would literally get, well, I would have, this is precisely the action of pi of the parity operator. But now we can go even one step further. So now I can define the second object conjugate. I can say an NQ manifold is a supermanifold with a right action of this supermonoid. So how do we go home? Odd line, and odd line. And again I have to say such that -1 acts as parity, as a parity operator. And this thing contains, it's even part of this, the body of this home is the ordinary home, which is this presented as R star. So this definition includes the n manifold, but it includes this odd direction. So then the well, these questions, this was maybe not the most common knowledge.
So I have a question, maybe naive one.
Yeah,
but,
please.
so what would be the problem in defining an manifold to be a topological space with a sheaf of n greater multigrams?
Well,
directly.
So okay, I think you're even more qualified to explain.
No, I don't think so. I don't think there is a problem really.
So there you have to say what that means precisely to be. No, like, I mean, how do you avoid that problem with having like infinitely many?
Well, if you have an n manifold, like non-negatively graded,
it always just gets higher. Just multiply two things in degree m, and then you get something in degree m plus n. So in every degree it's finite.
Yes.
right? And then there's a problem with like,
But
if you were to define them like the direct sum of all these degrees, like the gradients, algebra, right? The direct sum of all the degrees. Then it may not be a sheaf, because like a direct sum is just finite linear combinations. Even if you have a direct sum of infinite many vector spaces, this is finite linear combination. You can have like an infinite cover of the topological space with something degree 1, 2, 3, 4 growing, and that would not be global overlap, it would restrict to this. So
Like, or if you have, like, let's say you have a space which only has one coordinate of degree 2, which is even. Now you can imagine that you would have like a, what is it? Like you take a bunch of disjoint unions of intervals, and here you take that coordinate, here you take that coordinate squared, you take it cubed, etc., etc. And if you take infinitely many of them, then on each set, this is a. I guess that's what you're saying, right?
The sum of these elements is not in the
Yeah.
direct sum.
Yes.
yeah,
Okay.
so it's something like a direct product of these things, and it becomes
Right. So that would be, yeah, like, well, that's just not a sheet. Is it a free sheet? Would that be?
Yes.
yeah, that would be pretty.
Okay, thank you.
No, thank you. That was at some point. Okay. So now, so in the first definition, I only used I didn't use internal home. So maybe, okay, let me rephrase the second definition such that it doesn't use the internal home. If you're, so just to bring up one. So equivalently, let's remark. Equivalently, you can split the definition. Equivalently, an NQ manifold with an N manifold with degree 1, well, operator, the vector field, 0. the correspondence. Okay, so the two generators of this. No, sorry. Of the underlined diff, which was living inside our home, underlined. So our definition of NQ manifold is that it has an action of this underlined home, but inside there is diff, which is a Lie group, Lie supergroup. The two generators of this correspond precisely to the Euler vector field and Q. So in this kind of remark, I can split the definition. I define the Euler vector field. I define the grading using this trick, and then I add Q by hand. If you don't like internal homes, you can phrase it like this.
Can I?
Yes.
Maybe stupid question. These internal homes, they are objects in the category, so super manifolds, right?
Yes.
So if you write inclusion, that's like a submanifold, or?
Yes. Yes.
Submanifold.
Yes.
Is that always true? Like, you have a subset of homes, then if you make internal homes, that's...
I mean, I was doing this just by analogy, but I think it should work. Shouldn't it work? Like it's like GL inside one matrices. Let's say that sounds like it. I mean, if there's any good definition of submanifold should make this into something.
If it's not true, we have a bad definition of submanifold.
Exactly.
I guess we can play this in this game with any abelian supermonoid.
Any abelian?
Supermonoid.
Okay. Yeah. Yeah.
Well, there is also this set of theorems from 70s, I guess, when you have a grading by abelian group, and then it will be more or less the category of such algebras will be equivalent to super algebras.
Super, like Z to graded.
Yeah.
Okay.
There is also this works of Mulatkov from Kohler supermanifolds.
I think I've seen this. Okay. Is there?
Yeah,
I don't have anything to say about it, but that sounds interesting. Thank you. Okay, let's maybe make a break until 35. Okay, welcome everyone after the break. Okay, hope the sound is okay.
How did you release that?
What?
How did you release that?
So, what did we do? Oh yeah, we do this. Okay, so now we have a formal definition of these things. Now to just make a remark that so we now study the action. So we study the action of this underlying internal home from the outline itself. Now, if you have groups, they can either act on manifolds or they can act on vector spaces in a linear fashion. So we have a representation. So just let's make a remark that similarly one can show that linear representations of this home, of this supergroup, are the same as non-negatively graded complexes. Non-negatively graded complexes. So, in terms of the Lie algebras, there is two generators. One of them will give you the return the degree in which you are, and the other one will give you the homological vector field that goes in the complex. Okay, we won't use this. Let me just say cochain complexes. Sorry. Okay, so now we define what the spaces are. Now let's talk about maps. now it's all becomes very easy because we have just an action of a group. So definition, a map of, and now we can do it two things at once. So let's say n manifolds or nq manifolds is a supermanifold map. Compatible with the corresponding group, or sorry, monoid actually. Call it group. So intertwining, so compatible with the action, intertwining in action of the monoid or supermonoid. In one case it's an ordinary monoid, and the other one is the supermonoid. So if we break this down, this is just to say that it commutes with the vector fields. Like it preserves the vector fields E and Q. Should I say it? Okay. This is the same. Supermanifold. We don't say that. I never say anything. But if we okay, so this is end of the star. End of the formal definition. And now let's go back to the. So we discussed how to define things formally and informally. Actually, the stuff that is going to follow is also pretty formal, but it's also easy to understand. So I will just star ends here. This is not very important for anyone, but. Okay, so now the main. Okay, so it remains to define. To have to maximize the amount of fun that we're going to have, there is one, like a third degree object, so we know what this is, and now we add one more structure, we add a symplectic form, and this thing will be the most kind of exciting bit. And this thing has been given many names in the literature, so let me give you one which is particularly good, but unfortunately not that well adopted in the literature, so it's time to adopt it. So fix an integer. Now let's make a definition. We say a sigma n manifold. Sigma stands for symplectic. You know, sigma. That's n stands for n, so it's a good definition. This is an nq manifold together with a Q invariant symplectic form of degree n. Okay, now a couple of clarifications. Where is this? Yes. So two things I should explain. So what Q invariance, probably not very surprising, this means that it's invariant to the action of Q. So if I take the lead derivative, 0. Equivalently, you can say that Q is a symplectic vector field. Now, degree n, so what do I mean by that? So it's a symplectic form, so it's still a 2 form. But by degree n, but this thing means that one way to say it is that if you act with the Euler vector field, it should get multiplied by n. Okay, so in this way I can reformulate it nicely using Q and E. Maybe let me clarify the second thing even. Like, okay, so how does this translate into like a more concrete example? Because sometimes this is confusing. So e.g., if omega would be something like this, and it will depend on some coordinates, it can be of different degrees. then what I mean by then wanting, if we want this to be degree n, then the condition is that if you take the degree of the function, so this thing also has some degree because it depends on the y's, plus the degree of ya plus the degree of yb is equal to bn. Okay, the moral is that you count everything, but as if there were no d's. That's what is happening when you use the Euler vector field. Okay, actually the Euler vector field commutes with the differential, so it will actually act here, splitting out the degree here. So it commute here, and it will split out the number here, and split out the number here. Okay, so there is no this has nothing to do with the form degree. This is really the Euler vector field degree. That would avoid any confusion. Does that make sense?
Is there some name for these degrees if you want to distinguish which one? Is there one like cohomological degree or?
Yeah,
Grading.
Grading.
Browser.
Yeah, I'm probably. I mean, many people have. I'm afraid that for this, many people have different conventions, so that's why I'm kind of avoiding them. And the only thing I introduce here is the degree of coordinates, which is the underlying one given in the n manifold thing.
But you said also form degree. No, you said like that.
Yeah, but I corrected. But form degree is number of the degrees. How many degrees there are.
And I think homological degree will add everything together as well.
Yeah, so because this is just a supermanifold, then like all the if you want to study commutative properties of the object, then you need to care about the total degree of each object. So this has degree 1 plus degree of y. So the total degree is unfortunately the sum of the degrees of all degrees. That's why here I want to be specific that here I mean only this. So if you want, you can replace the sentence by this one. It's ambiguous.
But this dy have nothing to do with any coordinates on the manifold itself. They would be coordinates
On the tangent
tangent
one.
one.
That's right. Yeah. Okay. And okay, so let me give you the alternative names that people how people call these things. Also called symplectic MQ manifolds, or vice versa. MQ symplectic manifolds, NPQ manifolds, and various other names.
But for P, we just cross on structure.
Yeah, no, but if you look at the definition, they require it symplectic even when you use P. That's why this is a kind of better definition. So that we justify the goodness of the definition. So like in this kind of world with differentials and grading, everything has a grading and differential anyway, so you don't need, the important thing is to say that it has a symplectic form and it's a degree n, and that's what's hidden in this very concise and very elegant notation. And
Should I use this notation?
well, he introduced it. Yes. I mean, why not? Well, okay. He introduced it. Okay, and then for the rest of this, because we will not be dealing with symplectic stuff, so let me just remind you that we will keep the same notation, same convention as before. For instance, let's say for a function f, we define it's a Hamiltonian vector field. So this is for people who really like to have everything including the signs. Hamiltonian vector field. I choose to do it in the same way that we had before. So with a minus here on the right hand side, that's kind of aligned with the classical. Okay, whatever. This is the definition with the minus. And the Poisson bracket of two functions is defined to be the Hamiltonian vector field of one acting on the other function. So these are the same definitions that we had before. Okay, and now the stage is set, and now we can prove finally some juicy statements. So let's start with this one. And the proofs here will be extremely short. That's the beauty of it. So let's say on an n manifold, if a degree, positive degree form is closed. Okay, I should maybe say, okay, let's maybe unambiguous. Let me. So if we have a form of degree n, it's in the same way as we had for the symplectic form on a sigma manifold. So if let's say alpha was n alpha, then n is not 0, and d alpha is 0, then alpha is also exact. So there is no cohomology in forms whose degree is bigger than 0. See, there is none. And the proof, I'm going to put it here, maybe here. No? Okay. Let's see if people can guess the proof. People don't know the proof. So, if I have a form that is closed, and I want to show that it's exact, so one way to do it is to construct the primitive. So if I give you a form, so alpha here was the differential form. I didn't say that differential form. So if I have a differential form and I'm supposed to give you a primitive, then that needs to be form of 1 degree less. So how do I construct a form of 1 degree less if I have a form? And I have the only ingredients that I have, namely I have a manifold and I have this Q and E.
IE, for example. IE.
Yes? So I can insert one of the fields into the form, thus decreasing the degree. The form degree, making a 3 form into a 2 form. Now, which one do I insert? Do I insert Q or do I insert E? So the answer is E. So let's see. So if I do, I will, as an educated guess, I will already include some numerical factor. So let's study this object. This is not, I can do that because n is non-zero. So let's take this. This is a form of degree 1 or less. So let's hit it with D. Now what does it give me? So I can use the Cartan formula, which tells me that, it tells me that DIE plus minus some complicated sign, but we know how to calculate it. We showed it. This is the lead derivative. But now alpha is closed. Okay? So if I have DI, so I have this guy, I want to trade it for this and this, but this is 0. So this is just lead derivative on alpha, which very conveniently is n times alpha. This is alpha. Hence I have a primitive. I have a form which when I hit it with D, I get the original one. Okay, so there is one interesting corollary of this, which says that on a sigma n manifold, the cohomological vector field Q is always Hamiltonian. Okay, so it means that there exists a function such that if the x hat is Q. So how do I do that? Proof. Well, remember that part of the definition was that this thing is 0. Part of the definition of a sigma and manifold. So using Cartan, what I use the Cartan thing. I get this one plus minus this one acting on omega. But omega is closed, so again the second term doesn't contribute. And this thing tells me that d of IQ omega is closed. So IQ omega is closed. And now what is the degree? So I want to use a preceding proposition. So there is one thing I need to check. I need to check that that it's of degree non-zero, and it is because this thing had degree which was bigger or equal to 0, but this guy has degree 1, which means that the total degree of this is positive. So in fact, sorry, degree of this was n. So I said we are on sigma n manifold. So this is n. Total degree is just n plus 1. You can check this. It's just, if you hit the Euler vector field, it just goes 1 by 1. It just really adds up the degrees, which is not. Hence, it's exact. H is the function. I will put h times that IQ omega minus d h. Okay. Or in other words, the obstruction for symplectic vector fields to be Hamiltonian is given by the cohomology, but there is no cohomology in the respective degree, so that's why this works. What is the degree of h? So this was degree 1, this was degree n, so this also needs to be degree n plus 1. Sorry, not also, this needs to be degree n plus 1. So degree of h is actually n plus 1. So remember, here I'm talking about the degree again in the sense of this Euler vector field. Okay, so that's why I'm not counting the degrees of these objects, d and I, because as we saw before, when hitting this, your object with LE, you can jump over the differential. So this only counts. This doesn't care about the core degree. It only counts the Euler vector field degree. That's why I'm only adding this and this. I'm ignoring the d and the I. Is that persuasive?
So in fact, we have 3 types of gradient: parity, degree of form, and z gradient given by n gradient given by Euler vector.
Yes. I mean, yes, that is very yes. But here I'm actually so far I'm talking about this one. Okay. Proposition. This is a proposition intended for those who like science. So, if f is a function of degree n plus 1, just as we had there in an output, on a sigma n manifold, no, sorry. I'm speaking of the wrong proposition. I'm sorry. Sorry. If you have 2 functions and you calculate the commutator of the homological vector fields the commutator of the Hamiltonian vector field is the Hamiltonian field for the Poisson bracket. So that's one of the basic statements in ordinary symplectic geometry. So now I'm claiming that it goes through here without any signs in our conventions. This is an example of statement that's not surprising, but the proof will still be complicated, and including signs. But it will only be complicated because of signs, because there will be no other complication. So maybe a more pedagogically oriented person would kind of skip this and leave it as an exercise. I think part of conveying knowledge is also conveying the places which are painful. And in this case, it's just mildly inconvenient, not very painful. So let's prove that. let's just mimic the proof we had for the case before. So let's start by calculating this expression. So we want to start kind of from the right hand side. So we want to use we put there the commutator, the Poisson bracket, and let's calculate this. Let's see where signs emerge. So first of all, using the definition, this is just the Hamiltonian vector field acting in G, which is the same as a Lie derivative. Well, now Lie derivative commutes with D. Except what does commute mean here? It means that it commutes but with the signs included. So I need to take the quotient sign. So how does that work? So the result, of course, will be LXF dF, dG. But there is a sign. So what is the sign? I need to switch these two objects. Yes. So this one has degree 1. So now this is the okay. This is maybe confusing. So now we are working with differential forms. So as was mentioned before, the total the grading that determines the commutative properties of things is always the sum of all the degrees. So this object has degree 1, and this object has degree. First of all, Lie derivative doesn't itself carry any degree. And what is the degree of xf? Maybe let's check that. So let's me taking this copying the thing from above. So if this was degree n, and this was degree df, okay, then just mimicking the above. So this thing it will be so the degree of xf. Yeah, it's df minus n. Yeah. Why did I?
You mean the degree? Now it's the Euler.
Now it's the Euler degree. Yeah, but the
You
yeah.
should give them names. I mean,
Yeah. So this is the Euler degree.
Maybe you can write df and subscript.
because the total degree is differs by 2 from this. No?
Yes. Well.
Because there is
Well, yes
I
and no.
D.
Well, okay. So on functions there is only one degree, one n degree. That's unambiguous. That's the one given by the n gradient. Vector fields are kind of for us associated to functions, so it's like not. It doesn't carry any form degree. That's the convention that I'm silently using here. So this thing. So for this calculation, there is only one degree that I can mean by this. I guess that's what I was kind of silently implying. While here,
I mean, there is the form degree that we were discussing a few lectures ago, and D had degree 1, I had degree -1. So that's also a degree that you would associate with
Yes.
the object there.
yes, but okay. How do I get out of this pickle that I got myself into? So
For the science, it doesn't matter, no? So
for the science, well, okay, true, but it also okay. So let's say so here in okay. Let's argue this way. So what I'm doing here, this is now the working in the algebras of differential forms on my supermanifold. That's where I have these d's and Lie derivative living. So what I should and one rule that we know from there is that as far as this degree is concerned, the degree of this one is the same as the degree of xf, of the vector field xf. And the degree of vector field is simply the one that if you hit the function with it, how much does it change the degree of that function? And that should be calculated by this formula. Why is that?
this is the other degree that you just calculated, and the form degree doesn't matter on functions. Because functions are from degree 0.
Ah, yes, right. So this is a okay. Thank you. So this is a degree of a okay. But in this algebra, the degree of this operator is simply the degree of the vector field. Degree of vector field understood as degree that changes the degree of a function or not, and that's coincides with the Euler degree. So
Sorry for a strange question, but can we have in this definition something even, some even coordinates with odd degrees with respect to order? And
not coordinates, because we have coordinates only carry one degree, and that one is aligned with the Z2 grading of the manifold. We require that -1x as the parity operator.
yeah, okay, there's a, oh, right, yeah, I see.
So yeah, no, those things are there is no they are aligned. Okay, so maybe let me okay. So this is that minus n. And degree of a function is again unambiguous. Yeah. Okay. I don't know. Was this persuasive? No. Okay. I use two things here, right? One thing that I use is that the commutator of one thing I use is that the degree, now degree of operators, sorry, degree, now I should let me be precise, degree inside the derivation algebra of differential forms of some operator, like this. This was, we defined this to be, defined to be the degree of x as a degree of a vector field, if I want to be precise. And this just means that this is the degree of when a function, sorry, when I hit a function with a vector field, how much does it change the degree of the function? That's the degree of a vector field. And for us, it's the same as the Euler vector field, because, you know, like Euler vector, because it is. So this is the same as, this is the same, this just means that Euler vector.
Maybe we can calculate the Lie derivative with respect to Euler vector field of Lx, and then you will see the.
Okay, thank you. So yes, so important thing is on functions, the Euler vector field is the thing that returns the degree of that function. That's how we define degree of f. Sorry, f. So yeah, this is the only meaning that f can have. Now, if I want to unravel what this means, I should calculate deg xf minus deg f. Okay. And do I want to do, this is my definition of deg.
Maybe it's easy to act by Lie derivative on x applied to f, and then it will follow from the commutator.
Okay, good. So if I do this one on xf, right? This is Lex times f plus x times the degree of f. Degree of f times f. While this thing is degree of xf times xf. So by subtracting, we see that Lex is the degree of xf. Sorry?
Minus degree.
Minus degree of f, yeah, thank you. Minus degree of f, which is the definition that I gave you before. Is the way how much the x increases the degree of a function. So that's why this thing is the same as the Euler degree of x. that's
Yeah.
vector field.
Okay.
It's like
Vector.
degree in the sense of vector field,
We choose the Euler degree.
which is the Euler degree.
So what does it mean, degree in sense of vector fields?
Yeah, that means that it's the amount by which it increases degrees of function.
Okay, but it's the Euler degree of anything. It's kind of like that, no?
Well, I mean, yes. Yeah, that's
So
what
it's
I,
not
that's what,
specific to
that's,
vector
that's what I
fields.
painfully showed. That that's the
Yeah, but it's not specific to vector fields. It's just the Euler degree.
yeah, that's true. That's true. Yeah. So yeah. Okay. Yes. So okay. So slightly clumsy, but okay. So to summarize the rules that I use here, I use the commutativity rule in the derivations of algebra forms, and by those we define this operator to be an operator which extends the action of x in a way that it's a derivation, and it's a derivation of degree, which is the degree of the vector field. Now, the degree of the vector field is the same as the Euler degree of that thing. So that's why I calculated it here using the Euler degree. Good. So, okay, thing to remember is that. Okay, so now what do? I need to swap them. So I need to, I need to multiply it with, degree 1. Degree equals 1. So I have -1, and then I have degree big F minus n, and this whole thing multiplied by 1. Yes. Let's continue. What do I do now? And now I want to use the definition of a Hamilton vector field of G. So I eat 1 minus and the G, and I use this thing to rewrite this as -1 to take F times n, minus n, times becoming minus, oblique derivative xf on the insertion of xg into omega. Okay, I use the definition of the symplectic form of the Hamilton vector field, and now I want to use I want to commute them. Remember, so the formula that we have for commuting, if you remember, is this one. It says that if you have, that was the one which I stated as a proposition. There it's in the opposite order, unfortunately, which just leads to fun. Okay. It's not the other way around, without convention. So we need to swap, okay. I want to write this as so I want to well, whatever. How do I? So I want to get this is a I of right xg xf omega, but I cannot use it because there is a relative sign here, right? So this thing is ixly minus 1 to the degree, and now we have 1 plus degree of x multiplying 0 plus degree of y times ly ix. Okay, and now unfortunately I have the second thing, and I want to replace it by its iota of the commutator. So now I need to add this one sign with a minus. Okay, so I have what do I get? So I get this guy, deg f minus n. Then I get a minus, plus 1. then I get this thing. So here I get 1 plus degree of my vector field here. Okay, let me write here deg xg multiplying deg xf. And for these I need to substitute this one. Okay. So okay. By the way, here we are almost done, except we want this to be in the other order. So I need to comment that. But this is anti-commutative with the sign. So okay. So I will get okay, and there is some sign vector which is let me call degree of f p and degree of g q.
Degree of omega is.
Sorry?
No,
Oops, n.
you need also degree of omega.
That was n.
Ah, okay.
Yeah. So okay, so we have p minus n plus 1 plus 1 plus, and what is the degree of xg? Same formula. Q minus n times this guy, degree of xf, which is p minus n. And then I also need to have a sign which I get because I commute these two guys. I get 1 because it's antisymmetric. 1. And then I need to commute, so I need to take degree of xf and degree of xg, which are again q minus n, p minus n. Now let's see if this cancels. 1 cancels 1 because this is in minus 1 to the power. This thing cancels this one. Okay, p minus n is precisely what I get if I multiply this one. And this thing cancels with that thing. So I get what I want. I get xf, xg, end of proof. You see, it's just science. There's like nothing deep. Also, for this particular proof, maybe your sign convention was not the best, but it's it's the best for other stuff. Okay, now conclusion from this, or a corollary. Any questions today? So if you like signs like this, then come and work in like supergravity and BV form. It's usually better than the vector. Okay, so corollary. I will write what I started writing before. So if f is a function of degree n plus 1, so remember, I erased it, but the proposition was that on a sigma in manifold, remember, on a sigma in manifold, Q was Hamiltonian for a function of degree n plus 1. So let's look at those functions in particular. So if I have a function of degree n plus 1 on a sigma n manifold, then this thing is equivalent to xf squared equals 0. Okay, and this kind of almost immediately follows from the proposition, which I erased. Okay, so proposition said xf xg is x of fg. Okay. So proof. So first of all, notice that because the degree of f was n plus 1, which is larger than 0, or actually, sorry, no. So there are two conclusions that you can draw from this deep fact. One of them is that, well, the degree of xf is 1. That was the same here, right? Or you just use that formula. And what does this mean? It means that what I here wrote as a square was in fact the same as up to a factor as the commutator. Again, just to be super formal, so this implies that vanishing of this is equivalent to this thing being 0. Okay, this is just to replace the second condition. Now, second conclusion that we can draw from this is that what is the degree of this guy? So, okay, if you do the calculation, okay, so for each of the f's, they have degree n plus 1. So this together, if I only count the f's, then I have twice n plus 1. But applying a Poisson bracket lowers the degree by n because the symplectic form was of degree n. So Poisson bracket is always a dual object, it's an opposite thing. Or you can just look at the definition of Poisson. Okay, you can see. So this is 2 times n plus 1 minus n, which is n plus 2. Right? Yeah. Which crucially is bigger than 0. Because all our n's are non-negative integers. And this thing says that, okay, that vanishing of this guy is the same as vanishing is differential vanishing. Because okay, so here there is one subtlety here is that, you know, if this thing is 0, then this thing is 0. But if this thing is 0, it just means that the homological the Hamilton vector field is 0, which means that this can be constant. So the kind of the kernel of this map from functions to Hamilton vector field is given by constants. But there is no, but all constants live in degree 0 in our manifold. Yeah. So being constant and being of non-zero degree means that you are 0. And that's why, yeah. So now I just translated two sides of this statement into this, and their vanishing is given here. Or like the equivalent of their vanishing. Incidentally, this condition here, this is the famous, this thing is called the classical master equation. And it's the base point of BB analysis. Yeah, that's fair. Okay, so there is one. Okay, so as a consequence, we have a different, maybe more convenient characterization of a sigma manifold. So we can say that the sigma n manifold can be equivalently defined as an n manifold with a degree, with a symplectic form of degree n, together. So instead of talking about the differential, I can call it in terms of its Hamilton function. Together with a function, let's say h, of degree n plus 1, satisfying the classical mathematician. This is an equivalent description of it, but it's kind of much easier to tell you what a function is than to talk about vector field is. It's kind of like it's much more convenient in terms of data when you work with it. Because if you just say that give me a degree 7 function that's built out of these coordinates, then there is usually only a couple of ways how you can multiply things to make it work. So it's kind of very easy to assemble these objects. And then the only thing you have to verify for it to be a sigma manifold is this condition. Okay, brilliant. And okay, and maybe just to go towards the closure of this chapter. So we define what a sigma manifold is. So there is a sort of complementary point, not complementary, it's a bad word, like a accompanying notion. In symplectic geometry you have symplectic manifolds and you have also Lagrangian submanifolds, and they play an important role also in physics. So it's kind of good to define an analog here, and there's a notion called lambda structure. Lambda standing for Lagrangian. Just this sigma stands for symplectic. Wait, did I write note? Why did I write note? Definition. A lambda structure in a sigma n manifold is an NQ NQ Lagrangian submanifolds. Okay, so what does this mean? NQ. One way to say this is that like I guess you can say that the action of that monoid preserves that submanifold. Or if you want, you can say that E and Q are tangent to the submanifold. And you want it to be Lagrangian, so maximally half-dimensional. The tangent space should be half-dimensional isotropic. Let me not go into details here. Just say that this is kind of the natural notion. Some people would call it DG Lagrangian. It's compatible with differential integration. And so what we will see next time, I think there is maybe there's a couple of statements I can make, but then next time, which is in 2 weeks, we will close this course with giving you examples, which is the kind of where you should hopefully see that this thing is a very general type of thing, which actually encapsulates, and I would dare say simplifies many of the notions that people use in various contexts of geometry and algebra maybe. So that's what we will see next time. Like L-infinity algebra, Lie algebra, it's Courant algebra, it's all of that is neatly encoded in terms of these structures. So we will see that next time. We have something to look forward. Let me make a remark. Okay. So note. If we start with a sigma n manifold, so we have that this omega was non-degenerate. With sigma n, the symplectic form, sigma is non-degenerate, it is of degree n. What does this mean? It means that the map that we get between these objects, functions, vector fields, and manifolds, should be non-degenerate. Now, to be really precise, you should really see this thing as shifted by degree n, so that this is really a map that preserves the degree. So this is an isomorphism. But this thing, but what are the possible degrees in the Euler sense? What is the possible degrees of one forms? Well, they can, since the manifold was non-negatively graded, then this grading of this guy is in degree 0, 1, 2, etc. And if I shift it down by n, this means that this thing lives in degrees greater or equal to -n. So one conclusion you can draw from this is that there are, on a sigma manifold, there are no coordinates of degree higher than n, because if they were, if they were, like, otherwise the corresponding partial derivative would be of degree, it's always of the opposite degree because it removes one coordinate. So this would be of degree, would have degree less than -n, and it would live in here, which is not possible because they are the same. Does that make sense? So maybe more succinctly said, okay, so the way maybe just think about it. So omega pairs, it pairs some tangent vector with some other tangent vectors, and the way it does it, because it's a degree n, it means that it pairs these guys, where this is of degree p, with some other, just like in quotation marks, with some other guys, and these guys have to have degree n minus degree p. Sorry, degree of p, and degree of these other guys is n minus 2. So if you insert both of them in omega and you aim to get a number, a non-zero number, then they better be of complementary degree. That's why, if you have omega of degree 3, then it pairs coordinates of degree 1 and 2, 3 and 0, and that's it. So there can never be any coordinates outside. Therefore, by definition, there is no negative coordinate because we are working with non-negative graded manifolds. But because of the presence of the symplectic form, it means that we can only have coordinates of degree 0, 1, up to n. Let me write that as a sentence. Thus, on a sigma n manifold, there can only be coordinates of degrees 0, 1, up to n. So for instance, a sigma 0 manifold can only have coordinates of degree 0. So it's an ordinary manifold with a symplectic form of degree 0. So it's a symplectic manifold. There also needs to be a Hamiltonian function of degree 1, but if it has only coordinates of degree 0, well, it has to be 0. So sigma 0 manifold is the same as symplectic manifolds. We will repeat that next time. Okay.